Hello again, and welcome to Pre-Calculus, Section 1.2, Functions, the second lesson of Pre-Calculus. At the end of this lesson, I will be able to decide whether a relation between two variables is a function. I will be able to use function notation and evaluate functions. I will be able to find the domain of functions. I will be able to use functions to model and solve real-life problems. And I will be able to evaluate difference quotients. Let us proceed. First, it might be helpful to know exactly what a function is. So, from page 16 in the text, a function, let's call that function f, from a set, we'll call it set A, to another set, we'll call it set B, is a relation. So remember, a function is a relation. Now that relation assigns to each element x in the set A exactly one element y in the set B. The set A is called a domain, or the set of inputs of the function f, and the set B contains the range, or the set of outputs. That's the academic definition, but let's pause the video. Really try and think about what this term function means. Give yourself about 5 minutes to think about what it means. Okay, now that you've thought about it, what is an element? Well, it's like a thing. Let's use an analogy here. We'll think of a bucket of sand. So a thing or an element is like a grain of sand, and a set is like a collection of things, or a bucket of things. We're going to use a bucket of sand here. So an element in a set is like a grain of sand in a bucket of sand. Okay, so we're getting a handle on definitions here a little bit. So one bucket is called the domain, and a grain of sand in that bucket is given the name or variable x. The other bucket, the bucket is set B from the definition. That bucket is called the range, and a grain of sand in that bucket is given the name or variable y. So when you hear the terms relation or function, at least for now, think of equations. So an equation can also be called a function if, when I apply it to a grain of sand, x, from bucket A, I only get one grain of sand, or y, from bucket B. So let's look at this first table. Is this relation a function? And I ask you why or why not. So pause, give yourself a couple minutes to think about whether this is a function. Okay? Now that you're back, is it a function? I tell you, it is not a function. It is not a function. Not a function. Why isn't it a function? Well, remember, for any given any given grain of sand in the domain, meaning for any given value of x, the function assigns one and only one value for y. So I got the value 1 here, and I also got the value 1 here. Well, each time 1 turns into 4. So a value of 1 for x turns into a value of 4 for y in each case. No problems there. This could still be a function. However, when I get to the number 2, right? One time I put in 2 and I get 3. The other time I put in 2 and I get 5. So because 2 gives me 2 separate values, I cannot call this a function. Now if you notice, for 3, I only get one function. Whenever I put in 3, I get 8. And whenever I put in 4, I get 6. But these two values that I get when I put in 2 That's what makes this not a function. Okay? Now, give yourself a couple seconds, actually about a couple minutes, and think about this relation. Is it a function? Okay. You've paused the video, you've thought about it, and you've come back. And is this a function? Yes, it is a function. Why? Well, whenever I put in 1, I get one value. I get 44. When I put in the number 2, I get one value. I get 86. When I put in 3, I get one value. I get 35. When I put in 4, I get 7. So yes, this is a function. So now let's look at equations. Pause the video and think about both of these equations. Now, I've used function notation here, and we'll get into that a little bit later. But are these functions? Okay, you've paused the video and you started play again. Now you're ready to answer, are these functions? The top one, f of x equals x squared. It is a function. Why? Well, because for every value of x, I get a unique value for y. So when I put in -4 in for x, well, -4 squared is positive 16. If I put -2 in for x, I get positive 4, because -2 squared is positive 4. If I put 0 in, I get 0. If I put 2 in, if I put 4 in, I get 4 and 16. Now notice that my values of y can repeat. I got 2 4s and I got 2 16s. However, each value of x produces only one value for y. So when x equals -4, I only get one value, 16. When x equals -2, I get one value. I get a value of 4. When x equals 2, I also get 4. But for each value of x, I get only one value for y. And then the same thing goes with the positive 4 there. When x is positive 4, y is 16. So that is a function. Okay? Now, is this relation a function? Again, take a couple minutes, think about it, and think about it with the video paused, that is, and come back when you're done, hit play, and see what we agreed upon. Okay, you should be back now, and if you've thought about it, I hope you've come to the conclusion that this is not a function. It is not a function. Why? Well, let's look for x and for f of x. So when x equals 0, I can have only one value. The square root of 0 is 0. And there is no positive or negative 0. There is only 0. But look at what happens when I put x equals 1 in there. So what is the square root of 1? The square root of 1 is 1. But look at that thing right there. It can either be a positive 1 or a negative 1. And because of that positive or negative, because it could be either value, each value of x actually has two values for y. So this is not a function. It is not a function. Now, I made a mistake here. This actually, because this is not a function, I can't use the notation f of x. That is illegal. You can't do it. If it's a function, you can use it. If it's not, you can't use it. So don't get in the habit of using f of x in place of y unless that relationship or that equation represents a function. All right, let's look at notation some more. First of all, let's take the equation f of x equals 1 minus x squared. X is my input, and it is an element in the domain. F of x is my output, and it is an element in the range. So in other words, when I input a value for x, I get another output, f of x. And once again, the set of all inputs, all possible inputs, is called the domain. And again, the set of all possible outputs is called the range. Why do I use the adjective possible in things? Although f of x is commonly used, we can use other letters for our variables and for our functions as well. For example, h of t equals t squared plus 3t plus 16. That can be used to represent the height of a ball with respect to time. I choose h of t because h is a good letter to use to show height, and I use t because t is a good letter to use to represent time. Okay? We can also say in this example that height is a function of time. Now, let's take that equation and ask ourselves, well, what is height when time equals 2? Notice I haven't put units in here. I haven't done that yet, but you will. Trust me, you will. But when I say evaluate the function h of t when t equals 2, I can also write it thusly, right? Like so. I can write h of 2. So h of 2 here basically means I take this 2 that's in here, I took the t, right, and I replaced it with 2. So in my equation, everywhere I see a t, I replace it with the number 2. So that's what it looks like right here. H of 2 equals, well, t squared means 2 squared, so this maps down to here. This 3t becomes 3 times 2, and then 16 is just 16. So we take this equation, we simplify. 2 squared is 4, 3 times 2 is 6, plus 16, and then we add them all together and get 26. That means my height is 26 when my time is 2. We have just modeled a simple height versus time relationship. And yes, this is a function. Okay, now I want you to evaluate f of x equals 3x squared plus 5x minus 7 when f equals 6. Pause the video, work it out, and then return to the video once you're done, and we can go over it together. Okay, you've paused the video. Now let's work this together. So if I'm evaluating f of x when x equals 6, that's the same as saying I want to find f of 6. And that equals, well, I take everywhere I see an x in this equation, or in this function, I replace it with the number 6. So I take 3 times 6 squared plus 5 times 6 minus 7. Pardon my penmanship, it's hard to write on this board. Now let's simplify. Well, f of 6 equals 3 times 6 squared, which that is 36, plus 5 times 6 is 30, minus 7. Now I need to simplify some more. So f of 6 equals, 3 times 36, 3 times 30 is 90, plus 3 times 6, which is 18, so 90 plus 18 is 108, plus 30 minus 7, and that is 108 plus 30, that's 138, minus 7, that's 131, so f of 6 equals 131, and that is your answer. Box it and put a little dog ear on it and tell me that's your answer. So, we've talked about domains, but what's the academic definition for a domain? A domain is a set of values that a function works upon to produce another set of values called the range. Okay? Now, a domain can either be explicitly defined or implied by the expression. What do I mean by that? Well, when I say explicit, it means that the domain is written down. So, for example, a domain f of x equals 3x plus 6. Okay? That is a function. It's a specific type of function called a linear function. We've gone over it. However, I can restrict the domain here by saying for all x less than 3, meaning that the function follows this relationship only when x is less than 3. So, I can explicitly define my range. I can also imply it. How can I do that? Well, I can say, and I'll use a different letter and a different color, I'll use g of x. G of x equals the square root of x. Now, a couple things to be mindful of here. We have not gotten into complex numbers yet, so we are only looking at the real numbers. If you don't know what the difference is, we will get to that as well. However, knowing what I know right now, I know that I can't have a square root of a negative number. So, what happens here is my domain is implied, meaning for all x greater than or equal to 0 is the implied domain for this function. Notice that the stuff that I'm putting around in the box right now, that is not written. This is not written. All you have is g of x equals the square root of x. So you know that the domain for this is all x's greater than or equal to 0, because you can't have a square root of a negative number. So let's start figuring out what an implied domain is. Let's actually look at another example. Okay? So what do you think the domain for the function f of x equals x squared? What is the domain? Well, is there anything that you cannot square in the real numbers? No. So we would say all values of x. And there's different ways of writing that. You can say x, well, let me try this a little bit differently. I'll use an inequality here. We can say negative infinity is less than x, which is less than positive infinity. That's one way to write the domain. Another way of writing the domain is this. Negative infinity, positive infinity. This here is called interval notation. We'll go into that a little bit more later on. Yet a third way of writing this is to say that the domain of x is the set of all real numbers. And we got a fancy letter. It's basically a superimposed R, and that is the set of all real numbers. We'll get into more of that as well. So, how about the bottom? F of x equals 1 divided by the quantity x squared minus 4. What do I know about fractions? I know that I can't divide by 0. Division by 0 is not defined, so I can't do it. So I need to figure out what value of x makes this undefined. Well, I know that this is going to be either negative 2 or positive 2 will make the denominator 0. So I will say that the domain of this function is the set of all real numbers except x equals 2 or x equals negative 2. So those are the two values that x cannot be. All right? And again, when figuring out an implied domain of a function, ask yourself, what values of x will not work in the function? Now, let's talk about types of sets, because we haven't done this yet. There are bunches of sets that we use. This one, right here, the one I'm circling, we'll worry about in about 2 or 3 months. That's the set of complex numbers. So don't worry about that right now. However, the rest of these are very important. Take a minute and drill these into your head. The natural numbers. The natural numbers are the set of counting numbers. When you hold up a hand, you hold it up with a closed fist. That's 0. Then you stick out your thumb. That's the number 1. Then the index finger. That's 2. You got 2 appendages up. Then you stick up a second finger, so you got 2 fingers and a thumb. That's 3, and so on. And then after you get to 10 fingers, you keep counting past that by ones. 11, 12, 13, 14, and so on. Those are the set of natural numbers. This is the symbol that we use to annotate that. Okay? Now, add to that set all negative whole numbers. So, now we're talking from negative 3, negative 2, negative 1, 0, 1, 2, 3, all the way up between negative infinity and positive infinity, but only whole numbers. Those are called the set of integers. Integers is annotated with that funky looking Z. I forget why they chose Z. It's something to do with German, but I don't remember exactly what. So that is the set of integers. The third set is the set of rational numbers. Rational numbers are numbers that are resulting from any division of any 2 integers. So if you got an integer divided by an integer, that is a rational number. Okay? There are numbers that are not included in the rational numbers that we've talked about before. The most common or the most popular one is the number pi. It is not a rational number. It is what we call a transcendental number. And it's also a radical number. Okay? So, when we look at the set of rational numbers and we add in the transcendental numbers and the radical numbers, we get another set called the reals. And that's what this is right here. That's the funky R that we called into being before. And that is going to be any of these numbers above. So the reals include the naturals, they include the integers, they include the rationals, and they add into that numbers like pi and numbers like the square root of 2. Those are the real numbers. Again, the complex numbers we will get to later. I just want you to know right now that they exist. And I know you do from Algebra 2. More on those later. All right, so let's find the domain and range of this function. This is a function from example 6 on page 21. Okay, so find the domain and the range for this function. Now the domain is implied because it's not written down, right? Your job is to write it down. Okay, so the square root of the quantity 9 minus x squared. Well, can I have the square root of a negative number? I cannot. So what numbers create a negative number underneath the radical sign? Take a moment, think about it, unpause the video when you're done thinking. So for the domain, if I choose a number 0, let's choose x equals 0. Well, 0 squared is 0, 9 minus 0 is 9, and the square root of 9 is 3. I can do that. If I choose the number 1, well, 9 minus 1 squared is 8. So 9 minus 1, 1 squared is 1, 9 minus 1 is 8. I can do the square root of that. It's a radical, it's irrational, but it's not impossible. Okay? I could also do 3. If x is 3, I get x squared is 9. 9 minus 9 is 0, and the square root of 0 is 0. Trouble happens when I go above 3. Okay? If I do 4, 9 minus 4 squared. Well, 4 squared is 16, so 9 minus 16 would be negative 7, and I'm doing a square root of a negative number, and I can't do that. As a matter of fact, I can't do anything bigger than 3, positive or negative. So here is my domain. My domain is, let's write down, my domain is the set of all reals except negative 3 is doable, but anything greater than negative 3 is not, unless it's bigger than positive 3. So these cannot be done. Okay? I can't do anything. Let me back up. I can use any value between negative 3. Oh, I can use negative 3 as well. So I can do that. That is my domain. So I can do anything greater than or equal to negative 3, but also less than or equal to positive 3. Okay? Now, with the range, it gets a little bit tricky as well. And I wrote down this hint right here. So when you're given a square root sign without the plus or minus sign in front, interpret that as the positive square root. This is especially true when you see it written as a function, because I have to have only one value in the range for any given value in the domain. So my range here, well, all my possible domain are between 3 and negative 3. So my range is going to be somewhere between 9 and the square root of 9 and 0, but only the positives. So my range is going to be 0 less than or equal to y, which is less than or equal to 3, positive 3. And that is my range. All right, so let's look at the same problem, but this time I want to graph what the graph might look like. So here's what I want to do. I want to take a chart and graph all my x's and my f of x's. And I want to start with, we know it can't be negative, well, let's do negative 4 just to try. If I do negative 4 and I put negative 4 in for x, well, negative 4 squared is a positive 16. So I'm taking 9 and I'm subtracting a positive 16, And that means I get a negative 7. And then the square root of negative 7 is a negative number, and I can't do that. So I am going to not include that in my graph. So the function, the value of the function when x is negative 4 is not applicable. But when x is negative 3, or when it's positive 3 for that matter, so plus or minus 3, x squared would be 9, 9 minus 9 is 0, and the square root of 0 is 0. So I get that. Now, when x is plus or minus 2, I get 9 minus 4, so I get the square root of 5. And then when x is plus or minus 1, I get the square root of 8. So the square root of 5 is just over 2. The square root of 8 is just under 3. So here's how this graph's going to look. So when x is plus or minus 3, my f of x is going to equal 0. So right there and right there. And right here. Now, that's when x equals plus or minus 3. When x is 2, plus or minus 2 rather, I'm going to get a positive square root of 5. So when x is negative 2, that's just over 2 in the y-axis. So I'm going to put my dot right about there for x is positive 2 and x is negative 2. When x is 1, positive or negative 1, I'm going to get a number that is the square root of 8, which is just under 3. So I'm going to put a dot here and a dot here. And then when x is 0, and I didn't do that on my table, but when x is 0, 9 minus 0 squared, that's 9 minus 0, and that's 9. And then the square root of 9 is 3. So when x is 0, I get a 3 right there. My dot was messy there. And then all of the dots connecting, pardon my terrible drawing right there. And that is the graph for this function. So let's think. What is the range of this function? Well, the range is any number. So the range, remember, f of x is between, and I'm going to use less than or equal to, and we'll talk about that in a second, 0 and 3. And why is it less than or equal to and not just less than? Well, it's because that can f of x actually equal 0? Well, yes, it can. We know this because right here it actually equaled 0. And can it equal 3? Well, yes, it can. We actually know it can equal 3, as it does right there. So these are going to be less than or equal signs. And that is the range of my function. So let's talk about difference quotients real quick. Now, let's consider this expression right here. What does this expression represent? And I will use I'm going to use a linear function real quick. I'm going to do a linear function, so I'm going to draw a linear function like so, and I'm going to take a linear function and I'm going to choose a value for x. I'm going to use that in blue. So let's make that x right there. And then I'm going to take a value of h, and I'm going to make that, because they want to do h, I'm going to do h in green, and that means, and I'm going to do this x plus h right there. Okay? So x plus h is basically the sum of x and h, and on the number line we would show it like this. So what's f of x? F of x is, if I go up from x to the line, f of x is right there. If I go up from the point x plus h on the number line, I get to right here, and that is f of x plus h. Now let's do our lines so that I can label them thusly. So I got my labels for my graph. All right. Now, what do? Well, I'm taking f of x plus h. So this point up here, I'm going to do these in red. And actually, I'm going to do it in green. So this point right here is x plus h, comma, f of x plus h. So that is the ordered pair representing that point in green. And I'll do the other point in blue. And that point is x, comma, f of x. Okay, and that's the second ordered pair. So what, you might say? Well, look at what we got here. Look at what we got here. I'm going to do this in black now, I'm going to find the slope of this line, which equals rise over run, which also equals the change in y over the change in x. Well, what is the change in y? It is simply this one right here minus this one right here. That's my change in y. So let's write that. M equals f of x plus h minus f of x, and that's my change in y. Well, what is my change in x? Well, it's my x plus h minus x, right? Because this is my first x coordinate and this is my second x coordinate. So now all I need to do is simplify, and I can't simplify the top any. So I got slope equals f of x plus h minus f of x over, and on the denominator I got I got x plus h minus x. The x's cancel out, so I'm left with h. And that is what that equation means, or that expression. That expression is finding the slope of that function. And you might be thinking, so what? Right? Because we're doing it with a line and we already know how to find the slope of a line. But we're going to use this later in our class to find the slope of a parabola at any given point. This is the foundation of calculus right here. So lock this away in your memory banks. Thank you, and we'll see you next lesson.